Okay, now we go to fundamental problem 8.7. In this problem, basically you have a pipe, okay, embedded at this point, long pipe, and then you have another extension here and a pipe applied for 6 kN load. Alright, I'm going to draw everything. You cut here and then you try to find the internal loads. This one, to find the internal load, will be the same like what you have you had in P81, right? So I'm going to repeat in details those stuff. But generally what happens is you have 60 kN load, so you will have 60 kN load over here. Okay, that's the first load, transverse shear force of 6 kN load. Same goes to the handle, isn't it? And then this 6 kN load, if you take this arm, okay, 300 millimeter, of course this is 300 as well, but this 300 millimeter which will cause the torsion. So you have this torsional tau of 6 kN times 300, which is 1800 kN millimeter. So okay, the one which cause torsion, 6 kN times this 30, not this 30, sorry, not this 300, this 300, alright, will cause torsion. And then what is this 6 kN, but now you take this distance, 300 millimeter, okay, towards the section, and it will cause bending moment, isn't it? So you have bending moment of this, right? Okay, something like this, right? Bending moment, and then this is 6 kN times 300, which is 1800 kN millimeter. Same, right? So what you have is you have three internal loadings. One is transverse shear force of 6 kN going down. You have torsional moment of 1800 kN millimeter, right? And then you have bending moment, top tension, bottom compression, right? 1800 kN millimeter, right? So now of course, obviously, this one is V. This is V, isn't it? This is what? This is T, and this is V. So this one will result in shear stress tau. This one will result in shear stress tau. This sorry, this is M. This is M, bending moment M. Alright. So this one, this V will result in shear stress tau. This one, T will result in shear stress tau as well. While this M, bending moment, the bending moment will result in bending stress or normal stress sigma. Alright. But let's do this first, okay? And then this cross section is the circular cross section. Alright. This is this axis, X axis. Alright. And this is Y, this is Z, okay? This time around in this configuration, Y is along this pipe. So this one is Z, right? So this is X, this is Z. The inner diameter, this is a hollow pipe, which means that the outer diameter is solid, right? 50 millimeter. Sorry, not diameter, the radius, and then the radius is 40 millimeter. So you have the hollow diameter of 80 millimeter, alright? The total diameter is 100 millimeter. Okay, so let's look at the bending stress first. For point A, which is located here, so please understand this. This V going down like this, alright? V. This torsion goes this way, alright? So for point A, it goes up, right? Torsion. Bending moment. How does the bending moment go? Like this, right? I cannot rotate my hand. Going this way, right? So going this way, bending moment, alright? Going that way. So in this case, for this bending moment, what is the neutral axis? For the bending moment here, the neutral axis is this x-axis, okay? Alright? Understand that? Bending moment going this way, top under tension, bottom under compression. So this is neutral axis. Neutral axis, so the tau the sigma of A due to M, because it is a neutral axis, so the Y is 0. So in this case, your sigma A is 0 due to bending moment M. Okay, due to bending moment M. Right? Because it is located at the neutral axis, this point A. Alright? Okay, next, it goes to the second one, which is obvious. Tau A due to T rho of A over J. Right? So the T is 1800 kN/mm. What is the rho A? Rho A is distance from this to that one, which is C, basically. C out, C node, 50 mm. Isn't it? Rho is radius, so it is from the center to the point, which is A, which is point A is 50 mm. Alright. J is what? J is polar moment of inertia of this hollow circular shaft. So basically it is pi over 2, okay, I is pi over 4. Pi over 2 C node power of 4 minus C I power of 4. Alright, put that into the bracket. Or you can do it individually, but doesn't matter. As long as you understand, that's fine. 1800 times 50 pi over 2. C node is 50 power of 4 minus 40 power of 4. Okay, you hit the calculator, you get tau A equals to how much? 15.53 megapascal. Alright, and please understand, for this tau A, right? For this tau A, this point A, let's draw it, the volumetric element, right? This surface is the one which is facing you, this point A, alright, and then let's draw it to be a cube. Okay, remember, this is the surface. So what do you have here? You have the shear stress going up, isn't it? Because T goes like this. So A goes up, right? And the rest of the complementary stresses, this, and this. So okay. The main one is the blue one. Of course, the red ones are the complementary. You need to draw those complementary, by the way. Right? Okay, next, we look at what happened with tau A due to VQ of point A over IT. Okay? So V is what? 6 kilonewton, isn't it? So please understand this. For V, 6 kilonewton transverse shear force going down. So the neutral axis is this axis. Okay, this x-axis is neutral axis. So point A is actually lies on the neutral axis for this equation. Alright, so of course it is not 0, you have that one. And in fact the Q will be maximum over there. Right? So your V is 6 kilonewton. Your I, or you have not calculated yet, will be calculated very shortly. It's quite simple. Your T will be this thickness, but in fact you have to take both thicknesses. Alright? And then your Q, you need to, because this is along the neutral axis, right? And then you need to take this minus this. Okay? You remember Q is Y tilde prime A prime, right? So you need to take this A prime and then minus this A prime. Right? So let's do that. Okay, so first thing first, T of point A is how much? This is 50, okay, 50, this is 40, so this is 10, isn't it? 50, 40, this is 10. But again, like I said, you need to take the whole thickness, solid thickness, which is 10 and 10, which is 2 times 10. 20 millimeter. Please understand that. Alright? Even if you find here, it will be here and here. I mean, along a line which is parallel to the neutral axis, you have to take whole thickness, solid thickness. Okay? This is 40. And then for I, of course, I boundary axis, right? And this is circle, so it is simply pi over 4 c node power of 4 minus ci power of 4. Okay, please realize the difference between these two. For polar moment of inertia, for circle, it is pi over 2 c power 4 pi over 2. Okay, for I, moment of inertia, this is polar, this is moment of inertia, it is pi over 4 c power 4. Okay, so you just put the values like the one. Actually, you can guess. Actually, it's half of this. It should be half of it, but we didn't calculate. So, okay. So 50 power of 4 minus 50 power of 4. Sorry, 40 power of 4. Okay, and then you will get your I neutral axis as okay, 2.8981 10 power of 6 millimeter to power of 4. Okay. Alright. Okay, what else? You need to find the Q. This Q is quite tricky actually, but we will do it. No problem. So, for our Q, the first thing that you need to understand is, as the point A is here, the first Q is this. And then you need to subtract the second Q, which is this. Is it okay? Okay. The big one, the big Q, and then the small Q. You have to subtract them. Okay. And what is Q? Q is y tilde prime a prime, isn't it? Of course, in this case it will be summation, but one is positive, one is negative. So when you sum them up, this one is negative, right? What is the area? This is semicircle, isn't it? So pi over 2 c power of 4. C power of 2. Pi over 2 r squared, isn't it? Pi r squared, full circle, half circle, semicircle, it is pi over 2 r squared. Okay? How about y? Okay, this one is actually the one that you need to be able, you can derive again, but no point of doing so because you have that in the table. For this semicircle, alright, for the circle, the centroid will be here, alright, but for the semicircle, the centroid will be, look at the table, your data sheet. It is 4r over 3 pi from this axis. Alright, same goes to this one. Of course, this one will be this r, for this one will be this r. Right? For r over 3 pi, check that one. How to find the centroid of the of the semicircle. Right? So let's do this for QA. So for QA, right, this summation of y tilde prime a prime, okay, like I said, this one will be substituted by this one because this is minus area, this is the plus area, alright. So the first one is the big one here, which is 4r over 3 pi. So for r is 50, isn't it? For the big one, 4r over 3 pi, right, times the area, which is half pi over 2, half pi r squared, which is half 50 squared. It's okay. For r over 3 pi of 50 millimeter radius, right, for the semicircle, and the area is pi over 2 r squared. Pi over 2 because, or y over 2, because it is semicircle, half of the circle, right? And then you plus or you minus, as long as you do it correctly, the second one, second area, which is 4, the second Q, which is 4 r inner, inside, okay, 40, because it is the inner one, right, over 3 pi times pi over 2 times 40 squared. Is it okay? Okay, same formula, but this one is for 50 millimeter, right? This one is 40 millimeter, right? And you have to subtract this out because this is negative area, negative Q, basically, right? Okay, so you will get your QA to be 40.667 times 3 millimeter power of 3. Right? Okay, next we put this QA, I, and TA into the equation. So you put into tau A equals to V is how much? 6 kilonewton. Q is 40.7 times 10 of 3. Alright. We put more decimals. Alright. I is this 2.9 10 power 6. Again, put more decimal. The most decimals in your calculation, and T is 20. And you hit the calculator, you will find your tau A due to this tau A. Okay, this is tau A due to T. Okay, this is tau A due to V. So this tau A is 4.21 megapascal. Okay, now comes the tricky part. Okay, again, this is tau A due to T, right? 15.53 megapascal going up. How about this tau A due to V? Where is the direction? I mean, you got the answer 4.21 megapascal, but where is the direction of this? Okay, let me draw this surface first. Okay, again, this is the surface of A, right? So for this one, where is the direction? For this V goes down, right? Goes down. So everything will go down for V. The tau due to V everything will go down, including at point A will go down. So this tau A due to V will go down with the magnitude of 4.21 megapascal. Please understand this, otherwise you will get wrong answer later on. Alright. Okay. Of course, it's not enough. You need to draw the complementary stresses. Going up, then going back, going up, and going to the front. Alright. Why this is important? The reason is because, let me erase this first, because finally you need to find the final state of the stress. Alright, the final state of the stress. And what is the final tau A in this case? Can you see that? Okay, this is the face. Let's focus this face first. Okay, this surface A. Can you see that? Of course, in this case, there is no sigma. Okay, sigma is 0, so you don't have sigma. You don't have anything coming this way. But regarding the shear, are you going down or going up? No. Now we need to decide. You see, this tau A due to T is this much, 15.5 megapascal, going up, right? Due to T, going up 15.5 megapascal. While the tau A due to V, it is 4.25 megapascal going down. Alright? So your tau A, you need to understand this. 15.5 megapascal going up, 4.21 megapascal going down, so you have to subtract them out because they are in opposite direction, right? You can sum them up, but the thing is that they have different directions. So it is 15.5 minus 4.2. So your tau A is how much? It is 11.32. Understand this? You understand this? This one going up 15.5, this one going down 4.21 megapascal. So because directions are opposed, so you need to subtract them up, and of course it will go up. Okay, because 15.5 is bigger, you subtract this, and then it will just have the resulting 11.32 megapascal. Is it okay? So of course we draw the rest of the cube. Okay. Okay, draw the rest of the cube, and then you have this complementary shear. No, going this way. Okay, this is the one which is on the surface A, 11.3 megapascal going up, and this one, these three are the complementary shear stresses, right? So the final answer, first one is no shear, no normal stress at point A, okay, and the shear stress at point A is 11.32 megapascal going up. And please understand, and if you don't understand this direction, you sum this up, these two up, you will get wrong answer, right? Thank you.